Okay, 5.2. I lied in the last video and I said that mathematical induction wouldn't come for a couple sections. I was having a brain fart. We're doing math induction right now. So there are three things to talk about in this section. The first is we need to define the principle of mathematical induction. And the principle of induction really tells us how all of our induction proofs are going to work. And then we're going to look at some induction proofs, practicing. And then we're going to take a look at some properties with induction. Okay, so let's not beat around the bush here. Our principle of induction says, let P of n be a property defined for integers n, and let A be a fixed integer. The principle of induction says that we must show, number one, I call this the base case, that P of A is true. So you can think of this as a brute force. You're just plugging in what your A value is and showing that the property P of n is true. In the second part of every induction proof, we have what's called the induction hypothesis. Or this is also sometimes called the inductive step. But the induction hypothesis and the inductive step are one and the same. We need to prove, let's make this a semicolon. We need to prove if P of k is true, then P of k plus 1 is true. I don't know why I capitalized is. Bothers me. And every induction proof ends the same. We conclude that by mathematical induction, might write too big. And we're always mathematically inducting on n. P of n is true for all integers n. So there are two examples that are pretty classic when explaining induction. If you've learned induction in your pre-calculus class, which hopefully you did, you probably heard these. So induction is oftentimes compared to dominoes. And what you can think of is, let's say we line up our dominoes one after the other, standing up. The base case in the domino situation is showing that you physically can go knock over that first domino. You can just tap it and let it fall. The inductive hypothesis says if one domino falls, any of them that we've lined up, then the very next domino will fall. If P of k is true, then the next integer, P of k plus 1, also works. So if any one of our dominoes in our line falls down, the very next domino next to it in order will also fall. So if we know that we can knock over the first one, And we know that if we knock over one, the very next one falls. Well, you knock over the first one, that means the second one's going to fall. Since the second one fell, that means the third one's going to fall. The third one fell, that means the fourth one will fall, and that'll continue on and on and on until all of the dominoes are knocked over. Now, this is an infinite process, which is why we can claim for all integers n. The other example, to suit if you want a different example, is climbing a ladder. So the inductive idea is anyone can climb a ladder to the top. Your base case for climbing a ladder needs to show that you can get on that first rung. You can step onto the first rung of your ladder. The inductive step is showing that from any rung on the ladder, anywhere, not necessarily the first one, just any rung, if you're on that rung, you can step to the next one. If you can get on the first rung and you know you can step to the next one from any rung, then once you get on the first one, you can climb all the way to the top. Now, what that proof doesn't say, in a little funny aside here, is that you can get off the ladder. So that's where induction has its issues, is that it says nothing about stopping because it's all integers. So in the ladder example, you can climb an infinite ladder if you can get on the first rung, and you know you can climb from one rung to the next. But it doesn't say anything about getting off the ladder. Excuse me. So let's take a look at an induction proof here. So we are going to prove for all n and z, 1 plus 2 plus ... n equals n times n plus 1 over 2. So this is a classic summation property. If you add up the first n terms, it adds to this. And we're going to prove this. You most likely, if you saw induction and you saw series in your pre-calculus class, you probably proved this, but it's a good refresher. So if you think you know how it works, you can try. In general, I would recommend for this one that you don't pause it and just follow along with me here. So we're going to construct an inductive argument. So if we're going to do an inductive argument, we need to define our property, our P of n. So in this case, we're going to let P of n be the property 1 plus 2 plus ... up to n equals n over n plus 1 over 2. So we have our property. We need our base case. Base case starts with 1. So the base case is P of 1. So does 1 equal 1 times 1 plus 1 over 2? Well, this will be 2 over 2, which equals 1. Yes. So you can put a little question mark here if you want. The base case is always a brute force situation like this. You're just plugging in the first number. So the first property, not necessarily the first number. In this case, the first number and first property align, but that's not always going to be the case, and we'll see that in the next proof. So we have our base case. So now moving on to the inductive step, we need to prove if P of k and P of k plus 1. So we're going to assume P of k is true. That is 1 plus 2 plus ... all the way to k equals k times k plus 1 over 2. And this is for any k greater than or equal to 1. So now we're going to take a look at P of k plus 1. So then 1 plus 2 plus dot 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 plus k plus 1. Now we're doing something very specific here. We're not setting it equal to what our P of k plus 1 would be. Because again, we'd construct a circular reasoning and we need to make sure we don't do that. So this is P of, I shouldn't call it P of k, that's bad. It's 1 plus 2 plus dot 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 k parentheses plus k plus 1. Get this out of the way. So we know, we're assuming that this equals this. So we can rewrite this as 1 plus 2 plus dot 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 k plus 1 is k times k plus 1 over 2 plus k plus 1. And then we're just going to get a common denominator here. And we have k squared plus k over 2 plus 2k plus 2 over 2, or k squared plus 3k plus 2 over 2. This factors to k plus 1 times k plus 2 over 2. And we can rewrite this as nothing more than k plus 1 times k plus 1 plus 1 over 2. And this is what P of k plus 1 should say. So we can say, so P of k plus 1 is true. We've shown that directly. So now we have, if P of k is true, then P of k plus 1 is true. We have our base case. So we can induce mathematical induction here. So we can say by the principle of math induction, principle Did I spell that? That looks horrible. What's wrong with that? It looks so weird to me. Principle. Yeah, sure. I feel like I'm misspelling that. You can laugh at me silently because I can't hear you. Okay. So by the principle of math induction, P of n, which is 1 plus 2 plus dot dot dot, n equals n times n plus 1 over 2, is true for all integers n. So, a couple things to talk about here. Number one, yes, you have to have a conclusion like this. Just like with our proof by contraposition, you need to say why you can claim what you're claiming. And the reason why is math induction. By the principle of mathematical induction, we can say, now that we've shown the base case is true and the inductive hypothesis is true, that our property P of n will be true for all integers n. The second thing is about the body of the proof, which is this part here from the P of k. When you are working your induction proofs, if you do not use your property P of k somewhere in your proof getting to P of k plus 1, you've done it wrong. There's a reason why we assume this is true. If you don't use this somewhere in your proof, you have done it wrong. So that's an easy barometer to check with. Is if you're not sure when you get to the end of the proof, look at your work and see, did I use the thing that I assumed? We talked about this when we were doing direct proofs the last couple weeks. When you make an assumption, you should be using that assumption. Whether it comes at the very beginning or somewhere in the middle is a different question. But your inductive assumption here, P of k, is true, should be used somewhere in your proof. So, There's a term that the book uses for properties like this. So if a summation can be written with no ellipses or sigma notation, it is in what we call closed form. So closed form just means you can take a big addition problem and write it as a succinct expression. 1 plus 2 plus blah, 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 plus n is this nice thing. We saw this with the telescoping series in the last video as well. You can write that telescoping series as that one really, really big expression when we expanded it out, but it collapses down to the nice expression that we showed. So let's try another induction proof. There's some homework problems that are going to have you use this property to find sums, to find values of series, so keep that in mind. There's some other properties that are common. I can't remember if we talk about them in this section. Maybe in the next one. Or maybe you have to prove them in your homework. I'm blanking right now. But just know that they're going to call them closed form. So when you see that, know that they mean this. So there might be a proof that says, prove that you can write it in the closed form and then give you an expression. And they're just talking exactly like we just did. So let's do another induction proof. And this one's a short section, so this will be the last thing in this section. So we are going to use induction to prove the sum from I equals 0 to n of r to the I, this is an I, equals r to the n plus 1 minus 1 over r minus 1 for n greater than or equal to 0, and r is a real number such that r is not equal to 1. Right. So you've seen this before. This is nothing more than the sum of a geometric series. So we're going to use induction. I don't know why I put the line there. So we're going to first define our P of n. Let P of n be the sum from I equals 0 to n of r to the I equals r to the n plus 1 minus 1 over r minus 1. Now, at this point, if you're feeling up to it, go ahead, pause the video, and try and work this out on by yourself. So you know you need to do a base case, and you need to prove the inductive hypothesis. If P of k, then P of k plus 1. Okay, so let's walk through our base case. This starts at 0. So our base case is P of 0. So that is the sum from I equals 0 to 0, because it's P of n, so we're substituting 0 in for n, of r to the I. We know that this is just r to the 0, which equals 1. And this is nothing more than r to the 0 plus 1 minus 1 over r minus 1, because this is r minus 1 over r minus 1, which certainly, so we'll put a question mark right here, this certainly does equal 1. So we have our base case shown. Now we need our inductive step. So we're going to assume P of k for k greater than or equal to 0 is true. And that is that the sum from I equals 0 to k, r to the I, equals r to the k plus 1 minus 1 over r minus 1. So now we need to work on P of k plus 1. So we're not going to write out what P of k plus 1 is. We're just going to look at the first half. So this half of P of k plus 1. So that's the sum from I equals 0 to k plus 1 of r to the I. I don't want to write equals this half of k plus 1 because then we'll have a circular reasoning. So we want to make sure that we're just working off of this and we're going to get to our result. So this is where peeling the last term off like we did in the last section. So this is the sum from I equals 0 to k of r to the I plus r to the k plus 1. So we've peeled off that last term out of the series. And here's P of k sitting right there for us. So we can swap out this term for this term. R to the k plus 1 minus 1 over r minus 1 plus r to the k plus 1 times r minus 1 over r minus 1. Again, we have to use that P of k property. If we don't use it, we've done the proof wrong. So here we have it. We're going to add this up. R to the k plus 1 minus 1 plus r to the k plus 2, r times r to the k plus 1, minus r to the k plus 1, all over r minus 1. And so now the r to the k plus 1's cancel, and we end up with r to the k plus 2 minus 1 over r minus 1. But this is nothing more than r to the k plus 1 plus 1 minus 1 over r minus 1, which is exactly what we wanted it to be. That's the second half if you plug in k plus 1 into P of n. So, down. So P of k plus 1 is true. And by the principle of induction, P of n, which is that the sum from I equals 0, oh, you can't see that. The sum from I equals 0 to n of r to the I equals r to the, it's not k anymore, it's n plus 1 minus 1 over r minus 1. This is true for all integers n. But we have some restrictions in this problem. So n is greater than or equal to 0 because it was different. And r cannot be 1. That was our assumption. So that's the end of our proof. So just to reiterate a couple things when you're working on these proofs in the homework, you have to make sure that you are using your P of k plus 1 somewhere in your proof, or your P of k, not your P of k plus 1, that'd be bad. So this property that you assume true in the inductive step, you need to use that somewhere in your proof. We used it right here. Now, usually you have to do some work, like we did here, peeling that last piece, that end piece off of the series. You have to do some work to get the P of K to appear. Sometimes they're easier, sometimes they're harder. The first few in the homework will be easier, and they'll get progressively harder. There are some difficult induction proofs in this chapter. So keep that in mind, and there's a lot of resources online. You can come talk to me. You can talk to me in office hours. You can't come to me anymore. But almost every proof that you're going to do in the homework has been done before. So keep that in mind. And yeah, that's the end of this section.